Testindo di 2023 ini. Setelah 1 tahun kita vakum tahun lalu, kita mulai lagi untuk sesi webinar. Kali ini kita akan membahas tentang perkerasan jalan. Mungkin sedikit kembali remind ya. Di Testindo kita menyediakan peralatan-peralatan dan juga aplikatornya sebagai konsultan untuk pelaksanaan pengujiannya dan juga monitoringnya ya. Pada sesi pagi hari ini kita akan dapat wawasan dari Mr. Thomas Weinman. Beliau ini dari BDI Amerika, didampingi oleh Mr. Stan Smith dari BDI Amerika. Dua-duanya ini sangat senior sekali. Mr. Thomas Weinman sebagai speaker utama hari ini, Mr. Weinman ya, itu udah berpengalaman 40 tahun dan beliau backgroundnya teknik sipil. 40 tahun berpengalaman terkait dengan instrumentasi ya, terkait dengan desain, instalasi dan juga software untuk monitoring performa struktur-struktur dan geoteknikal, dan terkait juga jembatan, bendungan, tunnel juga gedung, stadion, wind tower dan struktur-struktur unik lainnya terkait dengan condition monitoring, kondisi kesehatannya, long term maintenance assessment. Dan beliau ini, Mr. Weinman ini juga merupakan perancang dari sensor di terkait performance sensor di BDI ini. Jadi memang kita akan langsung dengan perancang sensor dan instrumentasinya gitu. Beliau ini banyak sekali, ada CV-nya sama saya ini banyak sekali, panjang sekali ya. Intinya si Mr. Weinman ini profilnya teknik sipil dan sudah sangat senior sekali ya, dengan pengalaman 40 tahun. Kalau lihat nanti mungkin umurnya udah umur opa-opa di kita. Mungkin sebagai pendampingnya Mr. Stan sebagai bisnis development di BDI. Nanti kita akan bersama Bapak-Bapak, Ibu-Ibu. Saya ingat paparan nanti ya, ada pertanyaan silahkan di chat ya, boleh bahasa Indonesia, bahasa Inggris lebih baik. Nanti kita akan bantu untuk menyampaikan ke beliau biar dijawab pertanyaan-pertanyaannya. Saya langsung ini aja kali ya, langsung aja. Mr. Weinman, we are pleased to have your presentation, Mr. Stan. We can start the webinar now, please.
Okay. This is, can you hear me okay?
Yes, I can hear you.
Yes. Yes.
Okay.
Clear. Yeah.
Good morning, and thank you for your attendance and participation in this introduction to highway and airfield pavement instrumentation technologies. What we are talking about today is talking about BDI, Bridge Diagnostics, our pavement division. We purposes to gain a better knowledge of pavement performance. We're kind of, we provide this service to accelerated pavement test facilities, asset managers, owners, highways, and wherever the need is for better evaluation and understanding the performance of pavements and the underlying conditions. We feel BDI is unique in this because we are an engineering firm. We also are a manufacturing firm. We manufacture our own sensors and our own monitoring systems. And we also have extensive field experience, hands-on experience in utilizing these sensors. You'll see on a number of slides later on the feedback we get from the use of these sensors. We're constantly improving the sensors for the users to get a better product all the time. We provide installation services, training, complete system, turnkey solutions. We'll give you a couple of case studies that demonstrate these features, and we support these instruments. You know, we provide feedback and support to the owner in interpreting the data and understanding the data that is obtained for these applications. So this is a rare combination. You know, we're not just a sensor provider. We're not just a systems provider. You know, we provide the whole package through more than 20 years of experience. So the agenda here, what I'd like to talk about a little bit about is pavement testing, why we do it in the industry, pavement instrumentation, what type of instrumentation do you use for your pavement testing, the data systems and software available for capturing the and some new technology.
Sorry, Tom, your voice a little bit not really clear. Your voice, maybe internet, maybe.
Well, I'll try and get closer. Can you hear me better?
Maybe you can try to turn off your camera, maybe. Maybe
Yeah.
internet. Turn off your camera, maybe, to try maybe much better the signal.
Right.
Tom, can you turn off your camera?
Turn off my camera. Okay, maybe okay.
It might open up some bandwidth so your audio comes through clearer.
Yeah.
For me, it's not clear, Stan. What?
Same here. I think we're trying to resolve it.
Yeah, maybe.
Yeah, I have my camera. We just went back on one.
Yeah, maybe camera should be turned off.
Well, it's flashing.
It sounds clear, Tom. Why don't you proceed?
Okay. So you see the agenda that we'll talk about the various topics as presented on the agenda slide, and hopefully, you know, we can raise some questions and have some discussion and interaction. I keep trying to turn off my camera, but it's not. All right.
You're good. Seems to be a little better.
Have we, you know, how many people do we have in this? Is that any effect on this?
No, typically, you know, my solution is normally I turn off my camera and it seems to help. I could turn mine off as well. Just it's a bandwidth issue, I think.
Sounds clear from here.
Okay, because I'm trying to advance the slides.
But you sound much better, Tom.
Okay. All right. So my camera.
Sounds clear, Mr. Thomas. Sounds good.
You're good.
Good. So what you see here, where this all started is about 20 years ago, we had a contract, or I had a contract at the National Airport or National Aviation or Federal Aviation Administration, building a test facility for testing aircraft wheel loads on test pavements. So this is a quarter mile long pole barn with a big green machine that you see here, and it can simulate vehicle loads from any type of wheel configuration on any aircraft in the world. So they can change the wheel configurations, and they run this machine back and forth 24/7, and are able to test many different types of test pavements in series as this machine passes over and over. So during that process, we installed over 1,000 sensors, and they included all the sensors in green that you see that we now manufacture and provide to customers worldwide. We also utilize soil pressure sensors and soil moisture gauges from third-party vendors to provide a complete pavement monitoring solution. We build trackside automated data acquisition systems, worked with some of these facilities to help build their control room as well. So some of the other test facilities that you'll see here that we've also used these are different types of accelerated test pavement facilities that are single wheel loading. Starting from the upper left is called an accelerated loading frame, and it's a wheel that goes back and forth over test sections. The middle one is the Korean Highway Department, uses a circular test track. The upper right-hand corner is here in the US, it's National Center for Asphalt Technology. The bottom left is a Min-Road project where they reroute highway traffic over their test pavement sections. And then in the bottom right is the US Army Corps of Engineers facility where they use a wheel loading system on a pavement. So that's different types of load frames that you know, we've encountered as well as others. So how do you measure pavement response? You know, as you see there, you can have pavement instrumentation in different layers. You have your pavement, you have your supporting base layer. You can apply geogrid synthetics also in your below your base layers. And then there's sub-base layers. So what your interest is when pavements fail, when you see rutting or cracking and distortion of either flexible or rigid pavements, it's generally the result of the failure of the supporting foundation. In other words, your pavement fails because your base layer is failing, your geogrid, maybe you need geogrid, or your geogrid is not doing its job, or your sub-base layers are not going through the proper compaction during construction. So by using instrumentation in the various layers of the pavement structure, you can obtain a better response of where and why your pavement may be failing and at what stage, and helps you predict the service life of your pavement. So here what you're seeing is all the different possibilities, and of course there's others as well, and we'll go over all this instrumentation in further detail. So some of the sensors that BDI provides, and we'll talk about, you know, how we got there and what we do to improve their performance, but we provide asphalt strain gauges. We provide two sizes, you know, a larger gauge, which gives a bigger footprint, but it also, the cross section is a little bit taller. So in certain lifts of asphalt pavement, you may want to have a minimized height of your gauge. So we have a little bit smaller gauge, yet, you know, provides the same measurements, but in a shorter footprint, a smaller footprint.
Dan juga bisa sebagai bahan pengisi, ya. Jadi dia mengisi rongga yang ada di aspal. Kalau
And then, of course, we provide a vertical asphalt strain gauge as well, which will help us measure vertical strains in the asphalt layers and the lifts. And it's also a good sensor to use for triggering data collection. And we provide temperature trees to measure temperature gradients through either your rigid pavement or asphalt pavement layer, and through your base layer and supporting layer thicknesses as well. So these provide measurements at fixed intervals, and their input during construction or after construction, and they can either be thermocouples or thermistors based on what better interfaces to your existing data acquisition. We also provide a soil compression gauge, which measures can measure individual layer compression, either in vertical direction or horizontal. They can be built to specified layer thicknesses to measure the overall layer deformation in each respective layer if you put them in series, or you can use a multi-depth deflectometer which measures various subsurface deformations in each respective layer in one unit that is put in after the construction pavement is completed. And we'll talk a little bit about each of these sensors. So the first one we talk about is the asphalt strain gauge. So anybody who has worked with pavement instrumentation probably has all encountered that an asphalt strain gauge is one of the sensors that is subjected to the worst possible conditions. It goes into the hot mix asphalt, high temperature. You have a paving train that drags and pulls on the lead wires. You have a rolling operation, vibratory rolling and compaction. So the gauge is relatively fragile to the other sensors. When you put in all your pavement instrumentation, generally you have about a 99% success rate with all your pavement instrumentation, with the exception of asphalt strain gauges. So we've gone through a series of tests and improvements on asphalt strain gauges to make them more durable and to try and achieve that 99% success rate for the installation of the asphalt strain gauges. You know, some of these, these have been designed by me for more than 20 years and improved upon with, BDI technology that we have in-house. Some of the things that BDI only does for these asphalt strain gauges is we do NIST traceable dynamic calibration of these, which we also do with our regular strain gauges. So we have the in-house dynamic calibration capabilities. We also are a true sensor manufacturer. These aren't the only sensors we manufacture. We've been manufacturing sensors, strain sensors for more than 30 years. And this is just another time we do constantly. One of the recent improvements in the past year is we use now a new single gauge matrix as opposed to using two biaxial rosette gauges and wire these together in a full bridge. We have a custom built single gauge matrix that eliminates the fragile, delicate wiring between the different rosette gauges. And then we perform constant in-house research here at BDI, and we'll talk a little bit about this. One of the other things is you see the unbonded protective sleeve. Over our gauge and wiring, we have a brass sleeve that is part of the gauge, but it's unbonded. It does not provide any rigidity to the gauge. It just enhances its crushing of the lead wires, and all these things contribute to a much higher survival rate than normally seen with the use of asphalt strain gauges. I'm also a member of Transportation Research Board's Committee on Accelerated Pavement Testing, and I also chair a new subcommittee specific to instrumentation for pavement and geotechnical studies. Some of the continued in-house research that we have recently undertaken is doing temperature effects, placing these. We make mock-ups. Let me jump ahead. We make mock-ups in test beds here in our laboratory, and we do various tests. What we do here is we're testing out different types of compaction methods, and then we're running our wheel loads over these, collecting the data, making sure that we're getting back to our baseline information so we're not offsetting the drift of these as the gauge is being trafficked. So we do this in-house just to get a better feel for, you know, how to better recommend and improve on our installation techniques. So similarly, we do temperature studies with these as well. So we take an asphalt strain gauge, we'll put it in those pans, we'll put it outside, we'll subject it to a 24-hour temperature cycle, try and look at our potential temperature microstrain drift over that 24-hour, and you can see it's very well correlated to the temperature. So what this shows here is, you know, with this temperature drop, you're getting a tensile strain in the gauge. So what you're seeing is that this gauge, you know, the asphalt is shrinking, and when the asphalt is shrinking in that, you know, it's being restrained, the gauge is being restrained, it wants to shrink and it can't because it's restrained in the asphalt, so it shows an apparent tensile strain. So this is very helpful. This provides feedback to our users. When they measure this information, we can talk intelligently and have a better understanding of the data that they're seeing from temperature effects, and providing recommendations on how to provide temperature correction for these in unloaded conditions, and also to help them understand that if you're going to trigger your strain gauge, you have to have software algorithms that measure that drift and trigger based on a change of strain on a rolling average, not just a change in the strain, because the temperature can trigger your data acquisition system where you don't want it to. So again, you see our wheel loading of our ISO trainer staff too, so that they can help support installations and how to properly install these, and what to look for during the installation to support our clients. Again, here is our vertical asphalt strain gauge, and typically these can be used in asphalt or soil, and they'll provide a vertical strain under wheel passage. They're often used for triggering data collection or cameras. For concrete strain gauges, very similar. We've created, we use these for concrete, and again, we've created a single gauge matrix for our full bridge. These are full bridge strain gauges, so instead of using multiple rosette gauges with detailed wiring, we have a custom built single gauge matrix that we use that again makes the gauge a little bit more robust, and we use the same protective sleeve to protect it against vibration during concrete compaction. And here's some of our illustration of soil compression gauges. So what you're seeing here is a soil compression gauge that's placed in a base material before the top pavement is placed to measure vertical compaction under wheel loading. And you'll see how this all comes together on a couple of these case studies that I'll show you. And here's what's currently underway. We're trying to achieve the IP67 rating for the waterproofing of these. So what we've done is modified these soil compression gauges by putting O-rings in the sleeves where they meet. So we have these O-rings to make these submersible and IP67 rated. Right now, they're moisture protective. They're good in moist soils. They perform very well, but under, let's say, a constant submersion, we've had some recent requests for the use of these up north in our area under freeze-thaw conditions, where these could be totally immersed in high groundwater tables. So we're improving the water protection to an IP67 rating. And then we established quality control procedures that we utilize and encourage our clients to utilize, because when you buy the sensors from us, during the fabrication process, we're identifying and we're taking readings of these sensors throughout the fabrication process. And then we establish the calibration, and then we provide these reading sheets to our clients so that they continue with the readings, manual readings, which we strongly suggest up until the time of incorporating them to your data acquisition system. Because as you place the sensor, there's generally, in the case of an earth pressure cell, you're going to have various layers that are going to be placed on top. And you want to continue to monitor the performance of that pressure cell to assure yourself that you're capturing response of subsequent soil layers that are placed on top, and any rolling operations, compaction operations, as well as placement of your pavement. And if your sensor or your gauge is to fail, you really want to know when it failed, what's occurring, what's causing the failure, so that you can better prepare for the protection of that sensor for future placements. So all these have come from years and years of experience on how to best document the installation techniques and validate and prepare for the success of your sensor installation. And then here, for soil pressure cells, here's a couple instances. There's small 2-inch diameter pressure cells that are often used, as well as probably the more typical earth pressure cells that are about a 9-inch diameter pressure plate attached, filled with a liquid, compressible liquid, and measured compression with a standard hydraulic pressure cell. The bedding is most important. You want to bed it in sand. You want to protect it from point loading from aggregates. You don't want large aggregates on the front side of this pressure cell batten. You got to be careful when you place it directly under concrete, because the concrete can shrink away from the face of your pressure cell and actually remove the contact on that pressure cell until you have considerable traffic loading and settlement, so that that bottom concrete surface goes back to maintaining contact with your pressure cell. So it's kind of a tricky installation, and you should follow manufacturer's procedures, and there's you can make other improvements along the way, because most vendors really don't actually go out to the field and install these. So they give the best installation and recommendations, but there's a number of techniques that we've come across from our actual physical installations that improve our survivability and our measurability from these pressure cells. So here's 2 instances that for pressure cells that you need to be aware of. You need to be careful with the ring selection, because if you put a pressure cell down at your subgrade level, you want to maximize your reading of your pressure cell. You'll have, you may only be measuring 3, 4, 5 psi on that pressure cell, so you're not going to use a 250 psi pressure cell you're going to use maybe a 10 psi pressure cell to maximize the quality of your reading. But something to keep in mind, if you put down that 10 psi pressure cell during some operation, and you have heavy vehicles that are still weighing the material riding over that pressure cell, that pressure cell can potentially see on 50 psi wheel loads. So you can damage the pressure cell unless you protect it. So you optimally you want to choose a low-range pressure cell that optimizes your measurement, but you have to be careful to protect it from the high loads that could occur before your pavement is complete. Then the other thing is, should you calibrate your pressure cell? Because it's very well known if you read the installation of a typical pressure cell, then there's information, and they'll tell you that calibration factor should be, probably only about 10% accurate because of a number of factors. So it could be the actual soil you're placing it in, and the type of soil bridging that occurs. And then also, if you look at pressure cell closely in this picture, you don't have a perfectly smooth surface that your soil is bedding on. You cover it with some sand, but you kind of have a curvature, and then you have a stiff end around the plate, so that when the soil is being compacted, the soil is being compacted on the rigid outer perimeter of that platen, and the soft measurable platen is flexible, and it's flexing with the deformation of the pavement, and you're getting some shear resistance between the surrounding soil and the actual soil that's being compressed by the plate. So your calibration factor is not really that accurate right from the manufacturer. But what you can do is you can do field calibrations. So when you put your soil pressure cell in, and you put in your first lift of soil, you can put on a steel plate, you can put on a timber and a hydraulic ram, and if you're putting in these in similar soil condition, you can run a calibration of these, and you can end up with a multiplier of 1.1, or generally it's a higher multiplier than the calibration factor that's provided by the manufacturer. So if you want a more accurate measurement, you should calibrate these for the soil that these are being placed in. Soil moisture gauges, these are typically static measurements, maybe hourly measurements or daily measurements, and there's types that we've used in the past, which are the TDR gauges on the far left-hand side, but the more common gauge that's being used now is this new, it's a probe that we use. It's a 3-prong probe that we would recommend for use for moisture measurements. So we like that type of gauge, but either type of sensor, as long as it's adaptable to your data acquisition system or providing the data acquisition systems from the manufacturer for these type of moisture sensors. But these are placed generally at different lifts, in the soil, so you can measure, because moisture content has a big effect on the support of your subsurface conditions. So it's very important to understand the moisture content of the soil and how that's changing and how that's affecting your other sensor readings and the support for your pavement structure. And then here's an indication of our temperature trees. We can place these in the first lift of asphalt, drill a hole, and we can measure the different temperatures at different heights in the pavement to determine temperature gradients, because certainly the temperature on the top surface of your heat from the sun, but as well as being kind of cooled by your base course material. So it's important to understand the temperature gradient that's going through your flexible or rigid pavement surface. And then geogrid strains. We've used these, we've taken geogrids and we've instrumented these with strain gauges. It's a pretty detailed procedure. You have to protect these real well. Again, bed them in sand, cover them in sand before your next lift placement, and then certainly protect the lead wires. But the possibility, these are very delicate gauges, but you can certainly plan for success if you're using the right type of gauges, the right type of adhesives, and then the right type of protections over these gauges. And then there's a multi-depth deflectometer. So the multi-depth deflectometer, 20 years ago, when I was doing this pavement instrumentation for the Federal Aviation Administration, the only MDD that was available at the time was a BDITest MDD made in South Africa. And it's a series of sensors in series. It's a linear array. And the sensors are inserted into the ground. They're not replaceable. And it's a fairly complex installation. So the installation cost is fairly high because of the time especially if it's out in the public where you're doing road closures and traffic control. So about 20 years ago, I came up with a new sensor, a new design, which is a BDI sensor that we're using now, and it's a parallel array. So all the sensors are up at the top. They're in the road box. They're restrokable. So when you have rutting in your pavement and you started to exceed the range of your transducer, you can open up the road box and you can loosen those thumb screws and pull back on your transducer. So you can restroke your transducer to get a longer life out of these. So they're prefabricated to the soil conditions that they're anticipated to be used in. And typically we can install about 2 of these per day. The MDD cost is less than the previous design, and certainly the installation cost is much cheaper because less time out on site, less traffic control, much easier operation. Here's a kind of an overview of what comprises this MDD. So it's a number of pucks that have, it's very similar to the concept of an MPBX, a multiple position borehole extensometer, where you have anchor rods that are attached to your measurement points, and those anchor rods all go up to the top in the road box. In this case, they're prefabricated. They have snap ring anchors that lock them in place in the tube at their predetermined depths. So the rib tube provides a bonding mechanism to the borehole when it's placed. It has a hydraulic anchor down at the bottom that anchors it to the very bottom of the soil, at the bottom of your borehole. And then what you see in the last figure is the resettable transducers that are inside the road box at the top surface. So you can see how you can turn those thumb screws, loosen the transducer, and then restroke it and regain some of the stroke that you may have lost during the rutting of your pavement. Some of the applications, here's a brief sample of these. We've installed them out on rail tracks, slab track designs for rails, where we've put them, right adjacent to the slabs for the rails. And then we've installed them under ties and in the ballast, so you can measure the different deformations. As you notice here, we're placing these pucks generally at the interfaces of the soils. So, the change in measurements between, let's say, transducer 4 and transducer 3 will give you the compression in that layer 2. The same thing goes for the difference between the displacement in sensor 5 and 4 will tell you what compression is occurring in the overall fill layer number 3. So it's pretty simple mathematics to make use of the data from your transducers. Also use these out on haul roads and mines to measure rutting depth and the frequency of rutting depth that occurs. And here you see a figure that, again, when your pavement fails, it's the subsurface that's failing, that's allowing your top surface to deform. And what you want to know is what layer is providing that contribution and to what percentage of contribution to your failure mechanism. So an MDD will give you that multi-depth deformation under at various soil levels. So again, as we talked about the math, if these are placed at the interface, you can generate, what you're trying to measure. What is each measurement location? We call them ML4, ML3. It's a measurement location. So it tells you, what it's measuring actually, and then how to do the math. If you want to know what the sub-base 1 compression is, it's the difference of your reading of ML3 minus ML4. So it's simple mathematics to utilize this and find out what's going on in each of the respective layers. And then typically we'll complement this with a vertical asphalt strain gauge in the surface layer, because the road box, stiffens that area right there. So you really can't measure the deformation of the asphalt layer with the MDD, but you can do it with the vertical asphalt strain gauge and then utilize that with your MDD measurements to get a complete strain profile from the top surface all the way through your pavement and base layers. So installation needs for an MDD, as I mentioned, these are prefabricated. This is a recent project that we did for the U.S. Army Corps of Engineers. And we prefabricated the MDDs. We shipped them down. The toolkit that we use, it's a pump sprayer, a hydraulic pump for the hydraulic anchor, our kit of parts. We rent out these units too and provide instruction for users who want to install their own MDDs. And then you have a drill rig out there, and generally we push our borehole using a split spoon sampler. So it provides a very smooth borehole to insert the MDD. So once the MDD is placed into the borehole, we activate the hydraulic anchor with the hand pump down at the bottom, and it anchors the MDD to the base layer. And then we backfill the annular space with a mixture of sand and bend seal while feeding it with water from the bottom up with a pump sprayer. And then the bend seal expands and it grabs onto the hose and provides compression against the borehole wall and holds the rib tubing in place so that as the various soil layers compress, the MDD moves with the various soil layers. And then how do you get the wires out? When you install the MDD, the most typical application is what you see in the top center, is a slit trench is provided to the side of the road, and then you run your lead wires out. If it's just a 1-2 day operation, you might just have your lead wires protected like in the upper left hand. And then you can also pre-install your lead wires before you place your asphalt by putting in what we would call plywood knockouts. So we would pre-wire before the pavement is placed. You you pave the top surface, and then you come back and you remove the plywood knockouts, and your lead wire is sitting there buried in the pavement, ready for you to install the MDD in that void, in that knockout void. And then on the side, you see that, you're running your lead wires out of the road box through the slit trench. We're checking out all the transducers as we set them into the hole, and verifying their operation, their polarity, and it's just part of our standard QA procedures. And then you can incorporate weigh in motion and camera systems into your pavement monitoring projects also, and we'll illustrate with a couple case studies as well. Here we've installed a weigh in motion system. This is in a gorge and canyons in the western part of the United States. And we have a pretty large solar panel array. We're only getting about 4 hours of sunlight in this canyon per day, so we have a pretty substantial battery bank, large solar panels, but we also have a camera to power up, and we have a weather station up at the top, so we're capturing vehicle passage as it goes over our instrumented pavements, so we can better identify what is trafficking our pavements. So data rates, how fast should you be collecting data? And, it's certainly dependent on the vehicle speeds that you're going to achieve and what type of pavement, you're doing, because as you see on the far right, you have flexible pavements, and you have a zone of influence, which is about 1 wheel diameter, or actually about 3 wheel diameters for a flexible pavement. And for a rigid pavement, you have a zone of influence of about 8 wheel diameters. So what you want to do is you want to collect data in such a way that you can define the curve for that zone of influence. If you're capturing 4, 5, 6 data points over that vehicle passage, you can miss the peaks. So you have to collect enough data to define that curve very well. So little exercise shown here on the left. If you have vehicle passage at 50 kilometers per hour, which is 14 meters per second for a flexible pavement, it'll cover that 3 meters in 0.21 seconds. For a rigid pavement, it'll cover those 8 meters in 0.57 seconds, and respectively, for 100 kilometers per hour, you have half that time. So how many data points, if you collect data at 250 hertz, it'll tell you the number of data points you will capture in that time period. And really, you want 50 to 100 or more data points to make sure that you're capturing all your peaks. So a lot of times people will ask, how fast should I sample my data? Well, here's an illustration that we would recommend that people follow. So the equipment that BDI provides, it comes from our years of load testing. We manufacture our own hardware and for data collection. So we have 4 16-channel terminal nodes with sampling speeds up to 250 to 1,000 hertz. We have a monitoring, the brain box that collects the data from a number of nodes. We'll process the data, we'll store the data. You can do software algorithms for triggering the data. All this resides inside the STS4 brain box, so to speak. So we've used this for dozens of years for load testing applications, but it's also the perfect data collection system for trackside monitoring for pavement testing as well, because we can sample at the high speeds, we can build it nodally. We can build it down a test track. We can put a number of boxes, and we'll illustrate this with a couple of case studies. But then we package it all into a NEMA enclosure. So we'll have our node, we'll have our brain box, we'll have our communication, we'll have our other types of signal conditioning that may be required, integration of weigh and motion systems, etc. So we provide the complete monitoring system. And then, of course, we have data processing software. So we have, it's menu driven, really no programming involved. You start streaming data and it just starts collecting data, and you can click on the different sensors that you want displayed on your time history plots. And then you can do a range of filtering. We can do max min value extraction. So there's a number of options for the software. Very easy to use. Requires virtually no programming to get started right away. So you have data collection options. You can start out, maybe you're just going to go out there and bring your laptop and a logger, and you have a test site, and you have your lead wire coiled up in a box, and you come out twice a year and run a load test on your pavement. That's your most basic option with a laptop and a logger. You can also start in getting more complex, setting up a trackside system. It's more expensive, but then you got to start deciding how you're going to manage the data, how you're going to trigger the data, how you're going to collect it, when are you going to collect it, so it gets a little bit more complex. And then, of course, then you start dealing with how are you going to power the system. Is it going to be remote with AC or with AC power, or is it going to be remote with solar panel? So, all these things, and then how are you going to communicate? How are you going to pull this data, from these remote locations? Communication, hardwired communication, or is it going to be through modem communication? And then, the more complex, of course, is remote with solar power, with camera, so you've got communication, remote triggering, automated data downloading, and then you can do vehicle identification. And then, of course, we do, pretty sophisticated power budget spreadsheets, how to design your solar system, how to design your battery capacities, depending on where you are on this planet Earth and how much sunshine you get at those locations on a daily basis, how much time you can expect for downtime where you won't get sun. So through these little spreadsheets, we can, calculate the power budgets, power demands, and properly size our battery solar power system. So putting it all together, here's kind of a fairly complex, an illustration of, trying to compare three different test sections. You have various test sections, and what are you going to measure? You're going to put in your strain gauges on those top layers. You're going to put in pressure cells. You're going to put in your soil moisture sensor. You're going to put in your MDDs. So here's just kind of an illustration of how you may lay out a comparison study between three different pavement sections on the same highway, and for comparative purposes, you're trying to determine which pavement design performs the best. So we'll go through a couple case studies here to show some real life projects and how they were, how they were addressed. So here's a project in Indiana DOT here in the U.S. It had 22 flexible pavement test sections. The sensor quantities are listed here. What they were trying to do is evaluate comparison studies of 22 different test sections from various types of compaction, gradation of different types of material mixes, different ratios of cement stabilized bases, So again, they're altering the design, and then they're trying to evaluate the performance of those various design comparisons. So, a layout, would be a typical layout for these is identifying where you're going to put all these and how you're going to get all these sensors to the side of the road. So it's an illustration of utilizing almost all the types of sensors we talked about without the use of a weigh in motion system or a camera system, but we'll show that on the next one. So here, this is Honolulu Airport, and they want to resurface their taxiways. So what they wanted to do is remove the top section of their taxiways and place strain gauges in their new tops, resurfacing, and evaluate the performance of that resurfacing, and determine, do they go ahead and resurface all their taxiway throughout the airport. So they did one cold plane flexible test section. They put in 56 asphalt strain gauges, temperature trees. This is a completely remote system out at the airport. We had no power. We had to establish our own power, our own communication, and it also provides, we did the installation and commissioning, developed an operation and maintenance manual, and turned this over to the airport authorities. So in this, you see the asphalt strain gauges in the cold plane section. This is a complete remote section away from the airport. We ran our lead wires off the apron, solar powered system, modem communication, and we had a camera system that would capture the planes that were triggering our data collection. So we could identify, it's one thing to capture the data, but unless you have an understanding of what's providing this data, what type of wheel configuration, what type of plane, what type of loading, it helps to better understand the performance of your pavement. So this was a remote system, automated trigger, camera capture, and then remote data access. Here's another standalone system for Dallas-Fort Worth Airport, where at their servicing facility, they were going to repave all their service roads off, not in the airport, but right adjacent to their airport. So they had a design, they were trying to evaluate 3 different rigid test pavement sections. So over this red box in this area, they developed 3 different test sections, instrumented identically, and then trafficked and load tested annually to measure the various levels of degradation of each of the 3 test pavements. So what you see is this is how they're instrumented. You have 3 test sections down at the bottom, and the cross section of the test pavement, you have, it's concrete rigid pavement. So we have concrete strain gauges in the top and bottom layers of the concrete to measure any type of flexural bending that's occurring. We have pressure cells in the base layer immediately below the concrete surface, and then we have soil compression sensors in the subsequent in situ soil layers. So these are in the wheel lanes, so when the wheels go over it, you can measure that strain profile, how the force is transferred into the base layer, and how the soil is compressed in the in situ layer. So you can correlate that data very well and look at it. Each of the test sections are instrumented identically, so you're doing a comparison response study. And then here's something that we did for the Corps of Engineers, installing an MDD. Actually, we were working for Tensar. This was a project to evaluate the use of a geogrid to minimize a crushed limestone base. So typically a crushed limestone base might be 8 to 10 inches, but if you can use a geogrid, you can reduce the thickness of that crushed limestone base down to 6 or 4 inches, which greatly reduces material hauling in a large-scale project. So this was the test study that was done using an MDD to measure the compression in those soil layers and measure the effectiveness of the geogrid under wheel loading. And then here's another test track. This is a test track for Georgia DOT, Department of Transportation. Again, this is 18 different test sections, each with different types of geosynthetic. So it was evaluating geosynthetic support in 18 different test sections. These were all along the highway. So in each of the data acquisition systems, you know, each test section had 12 strain gauges, 4 pressure cells, and then each one had a trackside NEMA enclosure like you see on the right. So at each test section location, you had a trackside data acquisition system, and those were all interfaced to a central computer that would capture all the data, connected with a local area network with a camera recording system that would identify the types of vehicles that were passing over this highway system. So BDI also provides a cloud-based data management system that we use. You know, this was used on this project as well. We were capturing the data and posting it on a cloud-based system, triggered data, and we would measure also on the far right-hand side. We'd capture the weigh in motion system, and we would capture the type of vehicle that was going over it as well. So the image you saw here, this is the dashboard for the cloud-based system. And then this is also the dashboard where you can pull up the individual sensors and look at sensor response, time history. You can select the dates for the data you want to look at. Do you want to look at last week's data? Do you want to look at yesterday's data? So you can just, by typing in your dates from to, you can pull back archive data and display it, you know, from a web-based platform. So that's about it. That's, you know, that's the questions. I covered quite a bit on here. I don't know, you know, if you have questions. Did I go too fast? Is there, you know, what type of questions can I answer?
Tom, nice presentation. Thank you. There are some questions in chat room, but before I would like to share to you, so you can write also, but I don't know how to do that. Better you can read.
Stan, do you have access to any notes, or do you want to try and read the questions, or?
Wait a moment.
There's a lot of them, and they're not all in English.
Okay.
I sent to your email. I have already translated some.
Okay, let me.
Oke, Bapak Ibu mungkin yang ingin bertanya langsung barangkali ya, bisa kasih kode yang mau tanya langsung ya. Kasih kode aja di chat, siapa mau tanya langsung kasih apa, raise hand. You can raise hand, Stan akan kasih unmute sehingga bisa tanya langsung bahasa Inggris ya, kalau bisa ya. I have already sent to you all question in chat. Have you received with Tom?
Hold on, let me stop presenting. Engineering, I'm looking for the chat.
Yeah, one question from Anwar Rahim ya. In the relation.
Oh, okay. All right. I guess what I, yeah, I see the chat and
I could try to grab some of these questions. So here's one that can you explain more about temperature trees when it's going through asphalt and concrete?
So the temperature trees, you know, depending on the thickness of the asphalt, the thickness of the concrete, typically in an application for asphalt, you know, if it's a single lift, we would place the temperature tree in the base layer, and it would stick out into the asphalt where it's being placed. And then we would protect it with a shovel full of asphalt. Paving train would go over it, and those temperature measurements would be fixed. If your, you know, if your pavement or if your asphalt layer was 3 centimeters, you know, you might want to measure every centimeter. You might want to measure your temperature, or, you know, some fixed point, and it'll allow you to have a very fixed point of temperature measurement. In concrete, you know, we would do the same thing. We would, you know, typically make these temperature trees and drill a hole in the base layer and have these temperature trees stick up into the formed concrete. And then the concrete would be placed around the temperature tree, and it would be embedded in there. And then you could get the lead wires out to the side of the road through the asphalt or the pavement. We've also retrofitted these. We've installed these after the fact. So you can go and you can drill a hole in the top surface, but then you have to cut a slit trench and run your lead wire to the side of the road through the top surface of your pavement, or whatever your pavement material is.
Thank you, Tom. Next question is, how to define how many sensors and placement of sensors in one project so we can get a representative data that's valid?
Well, that's a tough question. That's, you know, as a bridge instrumentation engineer, we'll get a client and say, will come up to us and say, how should I instrument my bridge? Well, what's important, you have to ask yourself. I mean, you have to have a plan. You have to decide what you're trying to measure. If you're trying to compare different mixed designs, then, you know, the first thing is you should probably instrument those pavements equally. You should probably instrument them the same way. Like one of the case studies, you know, we have 3 different test sections. They're made differently, and you want to compare their response. You know, certainly what you want to do is you want to have redundancy of your gauges. I think you always want to put your sensors in your wheel path. I would suggest putting them in both wheel paths, so then you have a redundancy. If you lose a sensor, you can rely on the other sensor in the other wheel path. And then I would double that redundancy for asphalt strain gauges, just because everybody knows that asphalt strain gauges have the highest probability or the highest failure rate. You know, pressure cells, like I say, pressure cells, soil compression gauges, you know, if you do it right, you're going to have no problem. Your survivability should be 100%. For asphalt strain gauges, you can do everything that you can possibly do, and it's not unheard of to have failures of your sensors during the installation process for one reason or another. So the asphalt strain gauges, but you know, you want to put asphalt strain gauges longitudinally and transversely in a wheel path. I would put them longitudinally and transversely in both wheel paths, and maybe twice. You know, I would double that, and then maybe pressure cell underneath there, soil compression gauge underneath that. Or if you have a multitude of soil layers, use a multi-depth deflectometer in one of the wheel paths to correlate your various layer deformations in those wheel paths. So, you know, as you saw, let me go back to sharing since you're reading this. You know, so, you know, here's a pretty, you know, representative instrumentation plan for, you know, comparison of 3 different types of pavement design. One with GeoGrid, one without GeoGrid, one with different unbound granular material, one with different layer thicknesses. So, you know, it's addressing, each of the different layers, the support layers. It's addressing the pavement layers. It's addressing moisture content. It's addressing temperature. So it's correlating all that information together. So, you know, how you would do this, you know, this would be, you know, a typical example.
So there's a good question came in. The tools are highly relevant to empirical mechanistic methods that employ surface stresses and strains. Is there a BDI program like PenPave that can calculate the age of asphalt pavement for fatigue, cracking, damage, wetting, other deformation?
No, the answer is no. We do not do pavement analysis. We don't have software for pavement analysis. You know, we provide the measurements, the data acquisition, the sensors, expertise, installation expertise. We'll provide advice on sensor layout, but we do not perform detailed pavement analysis for prediction of cracking or service life or extended service life of pavements. The answer is, I guess, simply no.
There are two people has raised hand. Maybe would like to ask directly. Maybe you can give opportunities then.
Sure.
Silakan Pak Franciscus. Silakan langsung Pak Frans.
Okay.
Pak Franciscus minta suara siotang. Silakan Pak.
Looks unmuted.
Atau Pak Nur Rusandi mau duluan mungkin mau nanya. Silakan Pak. Okay, no. Maybe we'll prepare. Still prepare.
Do you want to try Nor?
There's a question. How long is the how many years the sensor will work after Pavement is done? Tom's.
Well, all right. So the answer or the question is how long, you know, will sensors last? I guess the answer would be, you know, it depends on what type of sensor and where it is. So typically the deeply embedded sensors, moisture gauges, temperature trees, soil pressure cells, those sensors tend to last great periods of time, many years, because when, you know, a pavement is starting to fail and you have deep rutting, you know, it's failing the sensor as well. So, you know, for perpetual pavement studies, if it's a perpetual pavement that's going to last, you know, for many years, the sensors should last for many years as well. The majority of our work or our clients are for accelerated test pavement facilities. So they are purposely trying to fail the pavement in the shortest period of time. So when they fail the pavement, it's through extensive rutting, extensive cracking, and in those conditions, our surface pavement sensors fail with the pavement. So if the pavement's going to fail in 6 months, the sensors are going to fail in 6 months.
There are some other question. Have you answered this from Mr. Anwar Ibrahim before? In relationship with the use of micro asphalt, how is the test system for mixed liquid asphalt with micro asphalt in the wrong mix composition? Example, AC base plus asphalt micro.
So they're asking about micro surfacing, Tom.
Well, if you can do microsurfacing, over an instrumented pavement, your microsurfacing, really does not affect, generally if you're putting in, let's say, asphalt strain gauges, you're going to put them in the bottom of your lift. So any microsurfacing that you do after, is really not going to affect the gauge. Your gauge should be fine, if that's what the question is.
And then we have a couple of different sizes to match the layer thickness we're putting it in, right? Right.
So if you're putting in, we have a gauge, typically we started out with this 8-inch gauge, and it has a height of about 3/4 of an inch. And then and that's good for any lift up until, 1, 2, 3-inch lifts. But then we had clients that were saying, we want to put in a 1-inch lift, and we don't want the gauge to stick up, to 3/4. We don't want it that close to the surface. So we came up with a new gauge that's about half that height. It's a 1/2 inch thick. So in a 3-centimeter lift, the smaller gauge would be the better gauge to use.
And then could you briefly explain the way the cameras work at highway speed?
So, the cameras, we have cameras that will, typically what we're doing is we're capturing snapshots. Although it's a video camera, we're capturing snapshots, a series of snapshots to identify a vehicle. We're not capturing a movie. Because the bandwidth, unless we had a fiber optic connection to the data acquisition system, the transfer of video movies through a modem communication would not be economical. So we're capturing snapshots, and those are usually triggered. They're triggered by either the weigh in motion system. They could be triggered by a pavement sensor. As it approaches, it triggers a relay on the camera, and the camera takes a picture, and that picture is time-stamped with the data acquisition system timestamp. So you can correlate the frames of the picture with the capturing of the data. You correlate it through the timestamping. And all this would reside, this is the importance of that core logger in our system. When we put together a system, see if I can get to this. So, when we put together a data acquisition system, this is basically a computer that's in the NEMA enclosure. So not only are you capturing your data and storing it on this, but you're also capturing any images, and you're storing it on here. You don't have to broadcast it right away. It can store it on here, and you can retrieve this data, during the night, with maybe your data rates are cheaper or your traffic is less. So, it's this brain box is what holds on to the data and the camera images and develops your triggering algorithms, etc.
Then I have a question that I'll rephrase. I think the question's driving at what kind of early indicators can be known of failures in the substructure based on this kind of instrumentation. So you mentioned rutting and
yep. Certainly the soil compression gauge, or the MDD, because what you're going to establish is, although you'll measure, we'll use the soil compression gauge as an example. So as a vehicle passes over the soil compression gauge, you'll measure a soil compression. And over time, that soil compression is going to slowly remain constant. It's not going to rebound. So over time, you're going to have a trend that's going to show a permanent deformation from that soil compression gauge or from the MDD. You're going to see a permanent deformation that does not rebound after vehicle passage. So that would be an indicator that you're getting permanent deformation in your soil layers that may not be visibly apparent yet on your pavement surface.
Thank you. We've covered a lot of questions. Is there any more?
Have you answered this question from Mr. Eka Sukarna, Stan? How is this tool used to test the density of the soil and top layer aggregates prior to placing the hot mix delivered?
So
go ahead.
No, go ahead, Tom.
Okay.
So I think what you're asking is before the pavement layer, is it used to, let's say, accept the quality of the placement of your base layers? Is that the question?
I think.
Yeah, I think, and then knowing that, would you change what you do on the surface density?
Yeah, well, I think, for compaction levels, I mean, you can identify with pressure cells, a lot of times you have to place your lifts at specified compaction levels. So, you measure the pressure that's going over your soil with pressure cells underneath it. And when you do your compaction, you can establish the type of loading that's going over there and how it's compressing the soil. So that could provide some information. I know that for a asset management project years ago, we installed MDDs before the pavement was placed. So we installed MDDs in the layers because during the construction process, what they wanted to know is, are they getting deformation during the continued construction, ongoing construction process from the heavy vehicle loads? Are they damaging their base layers that they believe were compacted fully? So we installed MDDs before the pavement surface was placed.
So it seems like the correlation is between displacement, deflection testing, and compaction, right?
Yeah. Yes.
There is a question also from Mr. Aris Adama.
Sorry.
Ya, Pak. Langsung, Pak.
Yeah. Sorry, Mr. Stan, because presented by Stan is of course very expensive for at the Bogor Regency PUPR, Pekerjaan Umum dan Penataan Ruang. Is this tool being used for project worth billions? Thank you.
So you're talking about the expense of the instrumentation, and I guess from a couple of questions, there was looking at what it takes to cover a large project that Tom was talking about, where you've got 20 or so test sections of various designs. And I think it can go down to much smaller sections that have sensors, and you'd have to be strategic about what sensors you picked based on what you're trying to evaluate. What are you trying to test? I'm not sure that answers the question, but
well, that's maybe a part of an answer. I would add to that, and I would say that it depends on the magnitude of what you're trying to do. If, a couple of these projects that like the Indiana DOT or Georgia DOT, they're going to implement a pavement design with or without GeoGrid, and they're going to implement this throughout their state for hundreds of miles of roads. So they're trying to make, they're spending money to make the best decision they can, because, you know, not that they would make the wrong decision, but they may select, without that information, they may select, you know, a secondary or a third best performance, which is going to require maintenance or asset management costs sooner than the other one. And those asset management costs would greatly exceed the cost of an instrumentation monitoring program.
What
So,
is the estimate price?
it depends on the number of test sections. It depends, you know, we're working right now with India on a big project in India, and India is undergoing the design for perpetual pavements. And what are they doing, Stan? I believe it's 6 test sections.
Yes.
So
And
This is related with planning, Pak. Jadi memang biasanya Pak, in bahasa ya Tom, I help. Biasanya Pak, untuk pemakaian sensor ini memang sesuai perencanaan yang kita rencanakan. Apa sih yang kita kritikal? Biasanya orang geoteknik dia kan yang merancang kekuatan, yang ingin mencapai target perkuatan di jalannya. Tentu dia tahu yang kritikal Pak. Di situ nanti dia mau monitor poinnya apa aja sensornya. Nah, sensor-sensor yang tadi disampaikan itu adalah pilihan-pilihan sensor yang bisa digunakan untuk monitoring. Dari sensor-sensor nanti baru dipilihkan elektronik yang sesuai. Nah, itu nanti harganya sesuai masing-masing unit sensor itu, dan elektronik yang digunakan, nanti ada powernya, itu harganya berupa sistem Pak, jadinya Pak, itu Pak. Kecuali Bapak mau beli sensornya aja, misalnya MDD tadi itu. Nah, itu harga MDD-nya bisa kita kasih kan gitu. Nah, jadi kalau ditanya harga memang tergantung apa yang diperlukan gitu Pak.
Pasti mahal harganya ya untuk ukuran kami di kabupaten.
Unit ini kayak seperti pusjatan itu Pak ya, punya unitnya. Ya memang kalau MDD itu ya kalau untuk satu unit gitu ya, tapi harus ada unit lainnya, itu ya nggak harus lelang ya, udah di 200 jutaan misalnya, itu dapat sih harga segitu Pak. Tergantung Pak, sensor itu ada yang murah juga, Strain Gate itu puluhan juta harganya gitu kan. Nah, tergantung Bapak perlu apa gitu.
Penggunaannya untuk proyek-proyek yang miliaran begitu Pak dari
ya betul. Sebenarnya ini lebih kepada proyek-proyek yang memang kritikal sih Pak, yang kita ingin pastikan kualitas performanya
jalan tol gitu ya.
Ya apa tuh, runway atau
highway,
jalan perkerasan highway misalnya, yang memang khusus gitu ya, yang ingin dipastikan kinerja dari geogridnya atau misalnya perkuatan jalan yang dirancang gitu ya, ingin dipastikan. Jangan dari pasang tapi masih failure, masih gagal gitu. Kalaupun gagal, kita harus tahu di mana gagalnya, kenapa. Itu kan makanya tadi ada kamera sekalian, saat kapan dia gagal, misalnya itu kan terekam nanti, terintegrasi sama kamera, sehingga saat jadi misalnya nilai lebih misalnya, kita tahu gitu visual lapangannya di jalan itu ada kejadian apa gitu.
Oke.
Ya.
Clear.
Ya, kebetulan memang hari ini ngebahasnya sensor sebenarnya Pak. Jadi kalau Bapak terkait sama misalnya proyek-proyek jalan, misalnya kayak alat-alat contoh SPT yang sederhana, yang memang bisa lebih cepat atau sesuai lapangan. Ada juga, mungkin nanti kita bahas sesi lain lah. Nanti saya share di WA nanti Pak.
Oke. Thank you Pak Joko.
Sama-sama Pak. There is some other question, Tom. I try to translate it. Maybe in bahasa ya, because the question is to me actually. Pak Jan Hes Nenggolan ya, TKDN alat ini masih kecil ya Pak ya. Kalau dibilang mungkin nanti di instrumentasinya itu softwarenya mungkin kita TKDN kan Pak, kalau sensornya nggak bisa kita TKDN, memang kita masih repot lah bikin sensor ya. Tapi di sistem instrumentasinya sama commissioning, training mungkin TKDN-nya Pak. Memang kita nggak sempat nih meng-TKDN-kan ini, karena TKDN itu kita harus mempunyai barangnya, harus ditunjukkan proses produksinya, lalu mereka asesmen gitu saat kita produksi itu. Sementara kita kan ini per project Pak. Jadi kita harus jadi pabrikan kayak BDI, baru kita TKDN, itu repot kita. Makanya kita nggak proses TKDN ini alat ini Pak. Begitu Pak Jansen. Pak Jan West Nenggolan. There is a question again from Pak Franciscus, Tom. If there were a rupture to subgrade, what kind of early warning indicator that can be used so we understand it is a warning?
Early warning detection for what? Failure of pavements?
He said
Seems that way.
To subgrade.
They use the word raptor. If there were a raptor to subgrade, what kind of early indicator that can be known early by this instrument? So it's a challenging question.
Yeah, I mean, other than, you know, as
But
we
I
talked
think-
before.
Yeah, go ahead. The displacement.
Yeah, the displacement, you know, the displacement, either an MDD, soil compression gauge, and trying to determine, you know, some sort of permanent deformation that's occurring, that is thereby, you know, weakening the support mechanism for your pavement.
Oke. Masih ada yang mau tanya, Pak? Kita masih tunggu nih. Kalau ada yang masih mau tanya langsung misalnya, boleh silakan. There's a question from Pak Abdul Halim. Is your sensor also work for reinforced asphalt pavement?
Yes. I mean, for reinforced, I mean, if it's, I assume you mean reinforced concrete, you know, we would use our concrete strain gauge. So we use the concrete strain gauge in rigid pavement. We would use the asphalt strain gauge in asphalt. And the reason for that is the stiffness of the sensor material is designed to match the stiffness of asphalt for the asphalt strain gauge. And of course, for the rigid pavement, we use a steel strain gauge, which is comparable to using reinforcing in concrete.
Oke. Pak Abdul Halim, kemudian terjawab ya. Kalau nggak ada pertanyaan lagi, mungkin
the other comment I would make is, you know, our asphalt strain gauges and our rigid concrete strain gauges, they're designed for dynamic measurements. You know, they're not vibrating wire gauges. So, you know, they provide you the ability to measure dynamic response, which, you know, a vibrating wire strain gauge will not allow you to do.
Okay. There's a question. How is the implementation in the mining road?
In mining roads, one of the examples I presented here.
Please share again, maybe your case study in mining road. You can explain maybe also how is the system of pavement and the sensor.
So up here in the upper right-hand corner, you can see the big Caterpillar truck. So this was a project for a a mining road in Gillette, Wyoming, and Caterpillar was selling their new version, their new supersized truck, bigger than this. And they were selling these to the mine operator. And the mine operator was very concerned that the bigger trucks would cause more damage and service to the haul roads. So Caterpillar did a design of the response of their wheel loads on their soils and said that, they predicted, the modeling results. And the mine owner said, well, that's fine, prove it. So we were hired to come out there and install MDDs in the haul roads, and the large trucks went over the MDDs and verified the model that was presented to the owner. So it was through confirmation of the model of actual truck response to the haul roads that provided the ability for Caterpillar to sell them new trucks.
Very good. There's a question on how to subtract the strain temperature drift from the total strain to get the mechanical strain in the pavement from the gauge.
So typically, if you're monitoring a strain gauge continuously, let's just look at the left-hand plot. So if there's no traffic on the road, this is the type of response you're going to see in 24 hours. And then it's going to repeat itself pretty much for the next 24 hours and the next 24 hours. And then when you have a vehicle that passes over, your vehicle response, this is a small vehicle. So this is, a truck tire that's going over this gauge. You're getting 600 microstrain over that. So what you're going to see is you're going to see an increase when a vehicle goes over this. You're going to see an increase at any point in time of 600 or 1,000 microstrain that will be superimposed on the temperature drift. So what you generally do is you trigger it based on a change in reading over time. So you're looking at a gauge and you're monitoring the strain level all the time, and really over this time there's no large increase in strain, no spike in the strain. So what you're looking for is in your software algorithm is you're looking for an increase of, let's say, 100 microstrain. And when that 100 microstrain occurs, you then capture your data for 3, 4, 5 seconds, and our data acquisition system provides a pre and post trigger buffer. So if it's triggered at 100 microstrain difference, it collects data and it goes back and says, give me the data a second before this happened. And then let's collect it for the next 2 seconds. So it does a pre and post trigger. So what you're measuring is you're measuring the response of the wheel load on top of that temperature change. Now, if you have a long enough history of this data, or if you have a control gauge that's not being trafficked, you can use this to subtract this data from your strain readings. So if you have a gauge that you put off to the side that's not going to be covered by a wheel, and all it does is capture temperature effects, well, that can be your temperature correction gauge. And you can use that gauge to subtract that strain reading from this and basically re-baseline this data. In other words, take the temperature out of this data by subtracting. If this was your temperature gauge, you would take this data presented here and you would subtract this value out of all your strain data. And then you would have more of a flat line, non-temperature affected strain response.
There's a question. What is pavement technology is used in mining, in this mining project?
I'm sorry, say that again.
What is the technology of pavement used in this mining area? In the mining road.
What is the
pavement technology like GeoGrid or something else?
No, it's not, because it's a constantly moving haul road. So, as they mine, that haul road might only be there for a week. And then they're moving to a parallel area and a new haul road is developed. These haul roads, for the example that I was showing in this mining operation, those haul roads are regraded about every 4 hours because they get such deep rutting from the constant traffic of these large trucks filled with coal. So the haul roads, a grader will develop the road at the beginning of the day, and this is a 24/7 operation. So, but sometimes the grader will grade the road, the trucks will pass maybe every 10 minutes, and then create ruts after 3-4 hours, and then the grader has to come back out, regrade the road. Well, in some instances, bigger trucks will cause the grader to come out more frequently. So what they were concerned about is these bigger trucks would cause more frequent grading or higher maintenance costs that would offset the advantage of hauling more coal.
Okay.
Now, another example, which we didn't touch on, and Stan and I have talked about it often, and because we're working with Canada, in some areas, in Canada is, for example, the Ministry of Forestry. So here's an industry, the logging industry, that at the beginning and end of winter, they cannot haul logs on the roads because of the freeze thaw. Because it's either too muddy, the ground is thawing and it's too muddy, or the ground is starting to freeze and it's too muddy. So they have to stop logging at the beginning and end of the season for about 3 to 4 weeks until the ground either freezes or it has become thawed and no longer soggy. So what they wanted to do is they wanted to reduce that stop time. If they can't haul for 3 weeks at the beginning and 3 weeks at the end, can they reduce it to 2 weeks at the beginning and 2 weeks at the end? So we instrumented those haul roads for the logging operations with MDDs to measure subsurface deformations that are related, to the freeze thaw cycles. Or, you could replace that with, a monsoon season or a rainy season, where you have ground that is weaker at those times of the year, and how can you establish the strength or deformation based on the moisture content in those soils at that time of the year. So if you were to install MDDs and moisture sensors, you could correlate your moisture content with your, ability to resist deformation.
Thank you for your explanation. I hope this clear. How to subtract the strain temperature from total strain to get mechanical strain in pavement strain gauge? They are sensitive to factors which interfere with the measurement, including weather and climate condition.
Well, yes. I mean, measuring long-term strain, you have the problem with the temperature drift, you have that problem, but generally what you're doing is you're comparing your strain peaks over time with similar vehicles. So if you have wheel loads based on, equivalent axle loads, so as you have, after 10,000 cycles and you have a measured vehicle, you have a strain value that is fairly consistently at, hypothetically, we'll say 300 microstrain. Well, over time, after 20,000 passes, maybe that value for that vehicle is going up you know, another 100 microstrain. So you're comparing your strain peaks based on vehicle passages. So over time, you're going to see an increase in your strains for equivalent axle loads. So once you say, you know, for an accelerated test pavement, it's simple because they always have, they know their load. It's the same load all the time. And they're running the same load and they're counting the cycles and they know they've got 10,000 cycles of this wheel load. They know they've got 20,000 cycles of this wheel load. They know they've got 50,000 cycles of this wheel load. So you have those measured peak, average peak strains at those time increments, and you plot that and you determine the degradation of your pavement based on axle load count passages and strain changes.
Okay. Have you ever installed the sensor in the pit area?
In pit?
Yeah, pit, like spiral area here is the soil is not stable. Pit.
No, I understand what Pete. I mean, I'm just trying to think because I've installed several hundred of the MDDs. I mean, it sounds like something you would use the MDD for because it would give you those subsurface deformations at various levels, and you know, your peat, you could identify where your peat layers are. But no, not to specifically address peat. No.
Ya, karena area gambut kan nggak ada.
But there's no reason you couldn't.
Yeah.
I think the trick would be anchoring it.
Right. You just might have to go to a layer because typically when you install your MDD, you provide an anchor at a depth that you are fully confident is, number one, is stable and it will not be affected by vehicle load because all your measurements reference that anchor. So if you're in a peat area, you might have to, you know, do some sampling to identify where can you go below that peat layer and establish a proper anchor.
Okay. There are another question from Anas Puri. You can read in question. In chat, you can check.
I'm looking right now. This is the last question here on, can we map some kind of reflective cracking and identify further cracking paths using your sensors that occurs in asphalt and concrete? So I know our federal aviation FAA is working on this exactly. And they are using asphalt strain gauges as well as other pressure sensors.
Our NDE has possibilities, our non-destructive evaluation group, not specifically our sensors, but they're doing machine learning, artificial intelligence, identifying cracks in pavements and in structures and identifying those cracks and looking for changes or growth of those cracks using cameras and artificial intelligence.
There are another question about related with the temperature effect for strain gauge. Still have a question from Pak Anas Puri. Maybe he still not get the point how to.
Should we use two strain gauges, one for measuring temperature pavement, another for measuring the strain effect of the temperature?
Yes.
And I think that's what you proposed.
Yeah.
And I think the other thing to point out is that we're measuring dynamic, right?
What's that?
Not like we're measuring the dynamic response of the pavement.
Yeah, typically that's the concern is your dynamic response of wheel loads. you're not really concerned, and how you measure, you're not looking at long-term strain change of the pavement. You're looking for long-term response under dynamic loading conditions for equivalent axle loads. After, as I said, after, you're doing typically, all these people are taking this data, and they're looking if they have a known wheel load and what is the strain response for that known wheel load after 10,000 passes, 20,000 passes, 30,000 passes, 40,000, and maybe it goes from 200 microstrain to 300 microstrain to 400 microstrain. Well, that's what you want to plot. You want to plot it's going from 300 to 400 to 500. You're not really, you don't really care about that long-term temperature drift that's occurring, maybe over the year or two that you're measuring these strains. That's really not, of concern to you.
Thank you, Tom.
Thank you, Tom. Masih ada pertanyaan,
We
Pak
have
Ibu?
about 5 minutes left.
Ya, masih ada pertanyaan mungkin atau enggak? Jadi ya.
I think we've covered most questions. Thank you,
Yes.
Tom, for an excellent presentation, and thank you for hosting this. We at BDI truly appreciate the opportunity to share this with you.
Yeah.
And we're available to answer specific questions.
I have a
going
last
forward.
question, maybe Stan. I have last question. Maybe this strain gauge is to measure also weight in motion also or not?
Well, you can use strain gauges for weigh in motion, but what you won't get is you won't get axle count. Well, you'll get axle count, but typical weigh in motions will have a software algorithm that will classify vehicles. So if you purchase a weigh in motion system from Kistler, we don't sell them, we use them, but Kistler or IRD or some of the weigh in motion manufacturers, it's, based on the spacing of your bars, your vehicle detection loops and all that, it detects, are you getting, 3 cars in a row, or are you getting an 18-wheeler? And the vehicle detection will identify that because it'll show an uninterrupted vehicle passage, meaning it's one long vehicle and not 3 vehicles in a row. And, it helps you better identify your vehicle classification. A strain gauge, you really can't do that with. I mean, the strain gauge will definitely tell you, if you go out and calibrate it, you put strain gauges in your pavement and you bring out a dump truck and you know what the vehicle weight is and you drive the axle over that strain gauge, you can then say that every time I get a peak strain of this, I can say a vehicle like that dump truck came by. So you can do kind of a classification in yourself saying, I had this many axle loads of this equivalent axle load that passed over my pavement. It helps you, where it really helps you is helps you identify overweight vehicles. So, if you classify, if you have your strain gauges down and you bring in the maximum load vehicle for that highway, and measure your strain response, and then if you exceed that strain response, you're getting overloaded vehicles coming onto your highway.
And I think one of our universities is working with their state DOT doing just that. They've got remote roads with a lot of farm traffic, rural traffic on, and they're they're using strain gauges and triggers of camera systems to detect those oversized loads.
Yeah, because based on those peak strains, you can turn your camera on, take a picture of it.
And these are sensitive. In the example Tom's showing here, going from left to right, the difference in weight between the front and back tires are evident, with the front being heavier with the engine on it, shown further to the left, and then the lighter load captured in the second peak there, and then the reverse as the vehicle backed back over the same test section. So they're quite sensitive.
And this is an SUV.
Yeah, it's a Toyota Tacoma.
So you can imagine, you know, getting a petrol truck or a dumpster or a heavier truck. You know, your strain response is going to be quite a lot larger.
Okay, thank you, Tom. Thank you, Stan.
Yes, and we're available to take questions at any time.
Yeah,
So,
you can prepare some questions and send them through to Stan, and we'll discuss them.
Absolutely.
Yeah, actually, I will send you an email. I have a question, but I will write everything in email, because the mining company come and asking for a solution. Okay.
Okay. We should.
Maybe
good.
we can close the presentation, Tom. If you have maybe short speech, maybe before I close this meeting.
Yeah, we will send the slides out as a PDF, so you can distribute it to our audience.
Yes.
And we want to thank everyone for taking time out of their busy days to attend this. And as I was just saying, we're here to answer questions going forward. So
Yeah.
thank you all.
Yeah, Stan,
Thank you. Have a wonderful day.
There is a request from Pa Abdul Halim. How if we take a picture together? Can you do that?
That would be tricky. Tom would have to stop sharing.
I can do that in Zoom, but I'm not familiar.
Yeah, I don't know if we could do that in Teams. So, but a good idea. Thank you.
Yeah, padahal ini orang tua-tua nih kita ajak nih. Maybe you can try to open camera. We can try. Coba Pak, kita open kamera. Let's gallery maybe. Nice idea. Okay. Oke. Terus silakan buka kameranya Pak. Kita ambil foto.
I will put this picture in your email reply.
Sistem engineering Pak siapa nih Pak? Sistem engineering Pak.
Thank you all. Bye. Bye.
Thank you.
Yeah.
Okay.
Thank you.
Yeah, we take picture ya.
Thank you, Mr.
And you can count down 1, 2, 3 and take picture.
3. Ready, set, now.
Now. 1, 2, 3.
Thank you, Stan, Mr. Tom, for your presentation.
You're quite welcome. Thank you for your attention.
Yes.
Okay, I'm going to end the meeting. Bye-bye.
Bye.
Bye. Thank you.
Thank you, Mr.
Videonya juga, PPT-nya. Kalau ada yang bertanya, mungkin butuh perencanaan terkait pavement monitoring juga bisa kontak saya. Terkait pavement monitoring,
Kok OP aku nggak bisa nge-zoom besar ya?
Oke, thank you. Terima kasih semuanya.
Baper aja, Gage.
Then can we end the webinar?
How?